Yeah, yeah, sure. So we're running late, so I'll try to do a relatively quick version of this. I know people want lunch. Pajama. Okay. Okay. Okay, good. Thank you. Okay, so first I want to express my appreciation for being invited to give this talk. This is a new field for me. I want to actually thank Professor Kang for helping push me into this field several years ago. So I'm still learning it, but I'm going to offer some ideas and some thoughts about it. So the intention here is it's a little bit different than what you've been hearing. It's more about circuits, and we're trying to invent new circuits and new problems, and there's a whole family of different technologies. Again, I'm from New York. I tend to speak a little fast, so I'll slow down. If you just raise your hand, I'll slow down. Okay, so there's a lot of different types of memristive technologies. We think this STT technology is fairly interesting. So I'm going to talk about specifically the STT. There's a lot of variety of different flavors, so we'll talk. So I'm just going to give a quick memristive review in the sense of a circuit approach. You've been hearing mostly about technologies, so now I'm going to be talking about circuits. Talk about specifically the STT the MTJ device, and then talk about a few of our research projects that are in play, that are in progress. We have more. So I'm just going to kind of give you a status quo of where we are on some of our interesting concepts, all at the circuit level. So again, there's four main points. I'm going to spin through this real quick because we don't have the time. But there's four major advantages of memristive behavior, the non-volatility being a big important aspect, the dynamic behavior, cost-effective fabrication, and CMOS compatibility. So, non-volatile, we all know what that means. Dynamic behavior, there's a thresholding aspect to it which we want to exploit. There's some feedback, control. Cost-effective fabrication. We can actually build this thing above the device, so it's kind of above the CMOS structure. People have mentioned the word 3D. It's not really my version of definition of 3D, where you've got multiple planes stacked above each other, but you can literally grow the magnetic material above the CMOS technology. Very, very efficient, very compatible. It makes it interesting. And so, not just on a circuit level, but actually even on an architectural level, you can do new things about how you want to blend these classical CMOS technologies merged with this MTJ technology. So it's interesting. So again, there's a whole family, important work being done in material development. This talk is intended just to review some ideas and thoughts at the circuits level, specifically the STT, which I'll explain in a second why I care. And CMOS compatibility, here are some nice pretty pictures showing compatibility, STT being built right above the CMOS plane. Okay, this is an important view graph. People have been giving different flavors of this view graph already today. This is my version of it. So there's all kinds of flavors of memristive devices. Can I see this? Yeah, not really. So there's continuous and there's discrete. There's bipolar, unipolar. We're looking at STT. It's a discrete technology. The definitions are here. It's pretty classical definitions of what these concepts mean. But STT, I think, is an interesting version of it. Why? Right here. So the main thing is that it's got a native digital behavior. It tends to lock onto either a high resistance or a low resistance, a high state or a low state. It's fairly high endurance to write operations. The only oxide breakdown is the only known failure mechanism currently understood. Again, this is currently understood as the operative phrase. These ideas are being developed and evaluated and created as we speak. The other thing that's kind of neat, and there's lots of applications where magnetism is interesting, is now you're actually integrating a magnetic material onto your chip structure, which offers other applications beyond just this memristive structure, like having RF applications and the like. And one of the things we're going to be talking about, examples of our research, is just that case. And has a fairly lower write current as compared to other memristive devices. It's still a problem. The write speed is a classic issue in memristive circuits. STT is a little bit better. Still bad, but a little bit better. Okay, so now let's just quickly breeze through the device behavior. You pass a current through the structure. You've got a domain, two different domain states, one's stable, one's not stable, and you force it to either agree with that stable plane or to be different. We call that parallel or anti-parallel. If it's parallel, it's got a lower resistance. If it's anti-parallel, it's got a higher resistance. That's it. So So, so the rest is just supporting that argument. So this is basically the concept. So it's kind of a classic definition of domain states enforcing those structures, and reminds me of those bubble memories back in the day for people who might remember that term. So we continue. We've got this free layer and this fixed layer, or pinned layer is another term they use. And you've got this tunneling oxide in between, and you can define the resistance simply by a high resistance or low resistance in terms of whether the currents are flowing in the same direction or not. And so we can actually force a switching mechanism by moving currents in different directions, and you can actually force a state that's either 1 or 0. So here's the dynamic. Interestingly, there's actually an oval structure that we use to describe it. And the reason you do that is you want to force a state to be what they call an easy state, either the top or the bottom, not to the sides. And so if you've got this unstable state in the middle, you can perturb it, and it's going to move to one of the two stable states, which is kind of nice. And so you apply this torque, and it forces these two stable independent resistance values. So that's the basic concept of STT, which is kind of nice. Okay, so now, again, I'm doing this quickly, I apologize. However, we've got different results we want to review. There's an issue of memory, which is the classic application because you've got two states. Sounds like a memory to me. But there's actually other ways you can apply it, and we'll talk about that in a few minutes. So just to review this quickly, some of the parameters, you've heard just about PCM and ion migration. The stability, the STT concept, we've got this range that's between 2 and 10K. That's actually the key point. So from a circuit's perspective, for the circuit designers and us in the room, and I'm sure there's more than a few, that ratio between the on resistance and the off resistance defines the ease of design. And the truth is, it's not good. It's 1 to 3, and it's a problem. And so and that's actually the weakness. So we were trying to offer circuit structures and circuit techniques to maximize, improve, to enhance that ratio, to make it easier to design. So that's the bad news. The good news is everything else is good. It's got a natural bistable state. The write latency is relatively quick as compared to other memristor technologies. The endurance is good, but that's the catch. That's the Achilles heel of the STT technology. And so that's where the circuit design gets interesting. So there are classical ways, and this again shows that image. In a memory structure, we've got a sense amp, we've got bit lines, and you can literally build this MTJ above this access transistor, which again, this doesn't work at all, but you can look at the word line and the transistor, and you can access, and that access device sets you up into the MTJ, and you actually fix that impedance, and that defines it. So when you read it or write it, you're looking at the current, which is going to be determined by the resistance of that MTJ, and that's going to be, that's important. So that difference in current is due to the difference in resistance, and therefore it's important to have a wide resistance differential. Again, I repeat some of the same points. It's CMOS compatible. It's an extra layer that you can add to the CMOS process, and it's back of the line. It requires about 3 more layers of masks, which is relatively efficient, and it sits nicely. So again, I don't look at this as 3D. 3D is those multiple planes, but it's clearly adding a third dimension or more material to the CMOS structure. So here's, so we've done some layouts of various structures. Now we'll talk about some of the ideas that we have. We've sized this, the access transistor to enable this bidirectional write current. We're trying to get some ideas and some thoughts about how to design this. So this is a basic cell and some cell structure. Now we actually added a diode to see whether we can enhance that resistive ratio, and we've done that. Now instead of 1 to 3, it's 2 to 10 times as great. The disadvantage is just a little bit more higher bit line voltage in a larger area. And we're looking at the difference in the sense current, which is when its resistance is high or low as a function of the bias voltage. We're trying to get a sense of how to design these circuits. So this is one structure. We did it with the diode. Then we tried it with the transistor. And now we're getting some ratios which are pretty nice, on the order of 60x. But of course, there's nothing free. It takes a lot more area, a higher bias voltage. And you can see again the sense current as a function of the bias voltage, and looking at the optimal bias voltage to produce the greatest differential in that resistance. These are unpublished results, I should tell you, but they're all being written up today. So hopefully they'll come out. We'll submit it relatively soon. So here's a layout. Continuing further. So now we actually opened up a new set of problems. So now you can actually redesign the RAM structure. and you built in this, this device, you've got this built-in gate structure, and now we're actually looking at ways to rechange the architecture to improve the access time and the write time, exploiting this differential in resistance between the high and low states. Okay, so that's, and here are some results of simulations we've done using a predictive model of 22 nanometer for various cases of power, speed, and so on. So we're trying to get a data set to actually analyze and understand the cell structure. We actually are working with a company with technology, but that's still in development as far as building it. Okay, for oscillators, this is, so you look at this hysteretic device, it naturally oscillates. So, so the idea is how can we use that built-in oscillation, the structure, and use that magnetic material for an RF application, which actually can exploit, have a nice little oscillator on chip. It's got very small area, it's got very high frequencies, it's tunable, it's got a very, very high Q factor, and we've got this magnetic material, so, and we're looking at building different multiple locking devices and to generate different overall oscillation frequencies. So this is some devices, ideas that we're developing. It's still in thought. I've actually talked to a friend of mine who's actually got some similar ideas, and he's actually already published something. So we're not going to be the first, but it's an idea where how do you exploit material for an analog and RF application, which is fairly interesting. We built some models, so that supports all this work. Professor Kang spoke earlier about some of the models. Xiaohao will also speak about some of his modeling in a few minutes. I think, maybe not. And so we built some Verilog analog models, and we exploit some of the classical expressions. I'm going to do some of these analyses. Okay, now in TCAM, we're actually a little more mature in this area. I've got a collaborator at my university who's actually been a fairly significant researcher in this area, Engin Ipek, pronounced Ipek actually. He's a Turkish kid who's doing very good work in resistive memories for, and he's developed this TCAM architecture. And he's a collaborator of mine. I do a lot of research with him, and so he's offered this new TCAM structure, which is kind of neat. It basically, it's meant for search. So you have a large signature, you've got a wide variety of number of bits, and you can determine whether you, by accessing the search line through these Memristors devices, you can determine, so you put a big signature across a line, you can do a very, very fast search and see whether you've accessed that state, and D and D bar defines whether you have or have not, and X is the don't care state. So we do that, and some of our work has been looking at how to explore it. The problem with this basic core is, because of that resistive ratio and the currents and voltages that we're operating with, it produces something on the order of a limitation of about 11-bit search signature. And that's too short to be interested. So we're actually looking at ways to expand that. And we're applying some of these diode structures. And we've actually shown that now we can actually look at 256 bits using this TCAM structure by integrating some of the back-coupled diode connected gates to actually provide a very high search environment. It does increase some of the power characteristics again. So that was too quick. Did I go too quick or what? Okay. So I apologize for that. But I recognize that at the time of the issue. So just to summarize, some of the classic technologies, the substrates are different. We use the polymer sometimes, ion integration. It requires additional mass steps. So STT requires an additional 3+ mass steps. The write currents are lower. People have actually built some of these structures, so they're shown here. These are in production, and these are some of the numbers. And these numbers don't, by the way, don't jive, don't go together. They're just points that we found in the literature to kind of give you some perspective on some of the characteristics of each of the technologies. But we've seen an order of a gigabit memory for STT. So people are doing it, and it's going to expand. This is production, recent devices that have come out. So just to summarize, STT, I think, is an interesting technology, more than others. There's a family of digital ways, digital structures, analog structures, memory structures. We've shown some examples of on-chip memory. We're trying to amplify that resistance ratio, which, again, we all understand. Basic circuit people understand that's an important characteristic. We think we've got some ideas. We haven't published it yet. We're the first to hear it, actually, literally. But we'll publish these in the short term. We're looking at some oscillators. Other people as well are looking at that. The TCAM is an interesting result. I think that's a very important result. It was published at ISCA last year, and it's a very clever approach. It's not mine, and we're trying to improve it and expand it and make it a little more robust. And we'll see where that goes. I think that's exciting, that TCAM structure. We've actually in the process of convincing several companies about the viability of that for a real production technology. To summarize then, STT is high endurance, low latency relative to other memristive technologies, relatively dense, very natural memory technology, but we're looking at other applications as well. And it's quite suitable to RF, has its magnetic devices, and fully integratable in the CMOS environment. So the question, I mean, you're going to hear a lot of different technologies today. The point of this presentation is SCT is a fairly interesting one. Again, this isn't my perfect area, but I know something about it, so I'd be happy to take any questions if you have any. One question if there is, if not, we can talk over Schnitzel. Okay, yes?
What about the linearity in the Memristor application? For example, you have to work very short pulses
Yes.
in order to get different levels of resistance.
Okay. Yeah, so to be honest, we don't know. That's the answer. However, if you're looking at a digital state, the linearity doesn't matter. So we're just trying to force a high state and a low state. I think relative to that question is the drift around that resistance in terms of variational effects to define that 1 and 0 state. So there's an element of how good a known resistance and how strong is that ratio. But beyond that, for analog applications, I think it's still a question. So linearity is an issue. It's not been well observed yet. We don't know the answer yet. So this is still an evolving technology. I don't know whether anyone else in the world has even looked at SCP for analog. So it's a fair question. I don't know the answer.
But you still call it a memristor.